Awesome. I'm really excited to be here. PyBay is one of my favorite conferences, primarily because I live 2 blocks away. So I could not, it is pretty easy for me to get here, but thank you for everyone else that came from further away to join me today. So let's kind of get going. Who am I? Or what do I do? That also. So currently I'm a professor at University of San Francisco. So it's the other San Francisco University. So we're at UCSF. I'm at USF. Very close, but different. I actually teach data science there. So I'm a full-time teaching faculty. And so that's kind of what I do. And so there's like a little flavor of like what I try to, how I teach. And what my primary life mission is to take complex topics and then give people an intuition of those complex topics and then empower them to kind of understand them and explore them on their own. So I'm just kind of like a guide through that journey. So deep learning has a lot of different definitions, and if you kind of ask different people, they kind of get different things. Some people are deep learning researchers, and those are the primary people that like understand and discover fundamental new things about deep learning. Other people are just practitioners of deep learning. Other people are just marketers for the deep learning hype cycle. What we're going to do is take kind of like a Pythonic approach to deep learning, and we're going to use the Keras library to kind of help us along the path. And so what is Keras? You could think about Keras like the request library. So everyone loves the request library because it makes URL requests so simple. It's intuitive, everyone understands it. Similar design principles were thought of for Keras. And so the notion is that, yeah, deep learning can be complex, but we can actually have a simplified way to interact with that. And that's what we're going to kind of talk about. And we're going to kind of define some easy neural networks. And we're going to kind of leave the execution of that to execution engines that are a little bit better than that. And so we don't have to go into the weeds and do all of that. You could also think about it a lot like SQL, where the fact that you could actually write SQL code, and then you hand it off to a SQL optimizer. The optimizer actually does a lot of the heavy lifting for you, and you could just focus on the business logic with SQL. Same thing here. We can focus on the deep learning logic and not worry so much about what's happening under the hood. Another thing is that it's a very modern library, so it ends up being very composable, and that makes it a joy to write code in there. And you're able to like write code that you understand, so then you're able to like kind of learn more quickly. And then also, if you get a little more knowledge, you're actually able to experiment much faster. And so those are kind of nice things. So it's kind of one of those things where it says low bar, high threshold. So it's easy to get going, but you're not going to hit the ceiling too quickly. So as far as the goals for today, I'm going to try to do a general introduction to deep learning. So if you've never seen deep learning before, this will be a kind of a way to get oriented to the landscape. If you've seen deep learning before, this will be nothing new. There's not going to be any math or any equations. So it's just going to be kind of a visual intuition of that. And we're going to talk mostly about the Keras library. And I'm going to kind of walk through an end-to-end example. So along with those goals, I have anti-goals. And so in no way am I equipping you to understand deep learning. That's a bigger thing than 45 minutes, but we'll get started on there. We're also not going to build a neural network from scratch. So in order to fully understand that, you need to go to the primitives and kind of assemble them yourselves, and then you fully understand what needs to happen. And then we're also not going to do a complete guide to the Keras library. The library is a very big, complete library. We're just going to kind of take the selected highlights of it. So again, a lot is talked about with neural networks. They're kind of created like the ultimate black box that we just hand them data. There's some kind of magic under the hood, and then out of that magic comes whatever we need it to do. That's not necessarily the case. So what we need to do is crack open that black box. And so what it is, it's a type of thing called a neural network that has very little to do with that neural part. It's loosely inspired on the brain. It has a lot more to do with the network part. So we're going to focus mostly on the network part. And what happens is we can kind of flow information from left to right. There's some notion of input. So there's input, and then there's this notion of nodes. Those nodes are active when there's input that it is associated with. And then there's connections that go through a series of hidden nodes. And then those hidden nodes learn patterns or learn representations of those that ultimately lead to the responses that we want. So it's a similar of an input to output matching, and then under the hood is a series of learned weights with that, and it just ends up becoming deeper like that. Also, it ends up becoming very, very wide, and so I actually would rather call it big learning because it ends up being deep and wide, but we're kind of stuck with the term for deep learning. Yeah? We're not going to do any of that. So the question is, hey, what about feed forward and backprop? I'm going to ignore those kind of technical terms, and so I'm just going to kind of skip that for now. Yep. And so what ends up happening is we look at each one of those individual nodes that we have right there, and we zoom in on it. What ends up happening is that each node has a set of inputs, which are represented by the X's. Those are activations. So how powerful is this thing? And then each one of those has a series of weights that are represented by the W's. So we take the activations, multiply it by the weights. So that's just a kind of a vector operation right there. And then we sum all of those together. That gives us the activation for the next node in line. And so that's kind of the fundamental elements of this. So what we end up is having some kind of activations and some kind of weights on those activations. And that tells the next node in line how important is this thing that we're doing. Then the heart of that is what happens is after we do that summation of activation times weights, we actually apply a non-linearity. And that non-linearity is the kind of secret sauce of deep learning. And so what happens is a non-linearity says that if we have a little bit of activation, we're going to have a little bit of activation, but then as we go up, it's not going to be a simple one-to-one or linear relationship. It's going to say that we might get to inflection points where that becomes increasingly important. And that's kind of what the nonlinearity allows us to do. The most common nonlinearity is the heart of logistic regression, which is a sigmoid function. So that's as technical as we're going to get for this talk. But the idea is that if we have this nonlinearity in there, we're able to learn nonlinear relationships. So the world's very, very complex, and oftentimes we can't model the world with simple relationships. This allows us to model complex nonlinear relationships through this notion of summation followed by a nonlinearity. And so what ends up happening is that we just repeat this pattern of activation, weights, summation, nonlinearity, and what happens is we just have groups of nodes. And so in a full neural network, there's actually going to be tens of thousands or even possibly millions of these stacked nodes that all have this kind of very simple building blocks of linear algebra. Cool. And so what happens is from these very simple primitives and having enough of them, what we do is we start learning the features of our data or what's important with our data. So in this case, we have a classic car right here, and we start learning low-level representations of that. And those low-level representations are around certain textures or certain lines. What we can do then is put together textures and lines and weight them in a nonlinear way, and then you end up with like kind of curves of a fender. Well, if you have these curves, you curve it more and more, you end up with a circle. Or in the case of if it's a cat, it would be an eye. And so it starts learning these low-level features at each one of these representations. And you can kind of see this is why we want a deep network, is because the deeper the network is, the more and more features that we can learn for the kind of different higher level representations. And the wider the network is, the more different feature maps that we can learn. And so we kind of put that together, and we're actually able to then kind of create combinations of that by taking little swatches from one part, little swatches from another part, put them together, and then we ultimately can create very complex images. Cool. So deep learning has revolutionized machine learning, and one of the reasons why it's revolutionized machine learning is this notion of learning complex nonlinearities in patterns of data. But another thing that ends up happening is that it actually automates much of machine learning. So instead of manually specifying which parts of the image I want to attend to make a decision about that image, I can automatically learn which parts of the image to attend to. And we call that kind of feature engineering or feature extraction, is saying what's happening. And so machine learning has really kind of adopted deep learning as this kind of fundamental technique because of this nature of like automatic learning. Cool. Okay, so I'm gonna pause there. So that is the general overview of deep learning. So now we're gonna kind of, once we get an orientation to the landscape, we're gonna jump into the Keras library. So one thing I wanna point out is that if you wanna follow along, you can go to that bit.ly link, but I also suggest that you type along. So if you're comfortable with Jupyter Notebook, you could spin up a Jupyter Notebook environment on your local machine. But I also wanna highlight 2 other projects that I think are really interesting for this kind of thing. One project is called Binder. What Binder does is that you point Binder at a GitHub repository, it loads in the requirements for that library, and automatically spins up a Docker container with the environment and the notebook in it, and then it's in browser. So there's no need to install anything. It'll just like load everything up, and you'll have a computational environment without installing anything on your local machine. So I think that's like pretty amazing. So that's that. One other thing I want to talk about is another new project called Collaboratory. So we all know and love Google Docs for spreadsheets and Word-style documents. Well, Google has actually released a project where you're actually able to do the similar thing for Jupyter Notebooks. So you're actually able to jump into an environment and kind of share it with other people and work through different examples together. Again, all in browser and shareable. So those are kind of nice things. So I just kind of want to highlight those. So while people are kind of getting that set up, they want to get set up, is there any questions about my deep learning flyby? What? Yes, so Google, the Collaboratory actually provides GPUs. So Binder is entirely CPUs and relatively underpowered. So it's just good for like kind of playing around. Whereas Collaboratory allows you to use GPUs for a limited amount of time, but you're able to train much, much faster. And so just one bit, there's a lot of jargon. Real quick, GPUs are graphical processing units originally designed to power video games, because video games are a lot of matrix algebra. Turns out that deep learning people also need a lot of matrix algebra, and they're able to co-opt GPUs to actually do the matrix algebra necessary for deep learning. Yeah.
Sorry, can you
okay, yeah.
so that everyone here listens?
Sure. So for noobs like myself about
Yes.
Jupyter Networks, can you just give like a quick 30-second
Yeah.
summary of it?
That's good. I skipped that too. So what Jupyter Notebooks are, it's an environment where you're actually able to like have a bunch of things all put together. So what we end up doing is if I spin up a new Jupyter Notebook right here, go over here. So what I'm able to do is have little bits of code that I'm able to interact with. And so what I have is I have our typical code editor like this that's able to run, but I can also switch very seamlessly into Markdown and write some notes for this. So this is like that. And so it's the notion of having a laboratory notebook that you would sketch diagrams, results, and do all of that. But this is kind of brought into the modern age where you have little bits of compute in a variety of languages. So in this case, this is Python. Also works well with C, Java, JavaScript, R. There's around 30 or more languages that are now available. And you're able to actually put notes in there. And those notes could be text, could be images, could be videos, could be interactive visualizations. So it's a nice way to kind of package everything together, and it's kind of the workhorse of data science. Cool. Other questions? Okay, let's jump into Keras, the library. There we are. Cool. So here is Keras, and the nice thing about this is that it allows me to kind of like run it live like that. And so what we're interested in is exploring this Keras library. So we can just kind of explore it as we go. And as we go right here, we can kind of see if we tab complete, there's a lot of different ways to do it. And so these are all the kind of modules that sit within, classes and modules that sit within Keras. And we're going to kind of explore a couple of them. What we're interested in first off is this notion of backend. And then within this, so I'm going to run this backend function. And so what this is saying is that we have this Keras library, which is an API or front end. So it's still code, but it's an API or front end code. And on the back end, it actually sends all the execution to another package called TensorFlow. So I'm going to do a quick sidebar on TensorFlow and then come back to Keras. So what TensorFlow is an open source library originally sponsored by Google to kind of be a generalized numeric platform. So the idea was to design something very, very flexible that could do a bunch of different things. So it could do deep learning. It could also do regular machine learning, but it's not limited to that. So the basic primitives are a notion of having tensors, which are n-dimensional matrices. So matrices are the standard kind of rows and columns of numbers, and those are in 2 dimensions. But you don't need to be limited in that. You could add a 3rd dimension. So you could have a cube, you have 4th dimension, hypercube. Those are all called tensors. And the notion of that is that those tensors then flow through a data graph. And at each node in that graph, some computation happens. So if you're familiar with matrix algebra, there might be a trace taken. Or we might transpose. Or we might do a matrix multiply by taking 2 different tensors and bringing them together and have the matrix multiply happen at that node. And so if you have that generic foundation, you're able to kind of create a bunch of things out of that. And so what happens is that you have this great flexible framework that allows you to do a bunch of different things. But the problem with that is that it's actually a sprawling library, and it's actually pretty low level because you're defining things at the scalar, vector, or matrix level. So at these lower level primitives, what Keras does is wrap up that library and expose a higher level library to that. So I can kind of define things one step up. So I can say, hey, I have this neural network. This is what the neural network looks like. It then translates that neural network into the scalars, vectors, matrices, and tensors that are needed for the computation without me having to specify the exact translation if I don't want to. Another nice thing about TensorFlow is that it's an execution engine that allows you to go to central processing units, so the standard kind of compute that are on most computers. Also these specialized graphical processing units. It's able to distribute it. So if you have one around, it'll use that. If you have more, you can do more. Also, it's easy to run the same code in the desktop, cloud, or on mobile devices. So Google's done a really good job creating all of this. Really solid, like lower level infrastructure that Keras then kind of sits on top. And so that's what allows us to kind of work more quickly. So what we need to do is have a task to kind of throw at a neural network. The hello world of deep learning is hand-digit recognition. This is an incredibly important problem if you are the United States Postal Service, UPS, or FedEx. People scrawl numbers on their packages. You want to have computer vision system that can then read those numbers or those scrawls and translate them into the appropriate numbers. So there's a corpus of these kind of numbers with labels called MNIST that are all these handwritten digits. Cool. So what happens, and what I mean by computer vision, is that we see the thing on the left. We see this kind of like fuzzy thing and kind of this like angled little line. And then we've seen so many of those that we have a mapping to the number 1. But we're trying to teach this computer that has never seen anything like this, or actually doesn't really see anything at all, to learn that mapping. What the computer instead sees is a matrix. So a notion of like rows and columns, and those rows and columns have intensity values. And so where it's white, the intensity is 0. Where it's high, it's 1 or black. And so what we're going to do is we're going to train a mapping from that matrix of numbers to a category. And that's that's at the heart of computer vision. And so what happens is, going from our data from like left to right, is that we have that input image that has 28 rows, 28 columns. We then stretch it out. And in this case, we transform it from a matrix into a vector. And so that's, if you do 28 times 28, 784, we end up with all of those activations for each one of those nodes. And then we're going to kind of percolate that through the system And on the other end, we hopefully have a system that learns to associate that scribble on the left with a category called 7. And so that's what we're going to have as a series of inputs. And then we're going to learn some weights that allow us to make the association between those pixel intensities and these human labels. Cool. So let's do this. So what it's going to look like in Keras is that we have Keras, and then we're able to like go into data sets. And Keras actually has a bunch of data sets convenient for us. Oh, it's not working for me. Nope. Type complete is not working. Oh, thank you. Yep. There we go. Let's do this. From Keras. There we go. That's our data set that we want. But you can see there's a bunch of other data sets that's in there. We're going to grab this MNIST data set. Cool. Now, a little bit of machine learning. So I tried to take out as much of the machine learning as I could out of this talk. But we have to talk about one thing, and this is called train test split. And so the notion of machine learning is that we want to teach computers to learn from data to generalize to data that we haven't seen before. Deep learning is incredibly powerful, and we'll just memorize everything we show it. And so what we want to do is have it be robust to just simple memorization of our input data. And so what we want to do is have a notion of training data and testing data. So we're going to have a little bit of study data, which is the training data, and then we're going to have a test. And really only care about how good the computer is at data it hasn't seen before or the test data. So we'll kind of set that up. And the way that we set that up is we say, hey, we have X train, which is our pixel values. And then we have Y train, which are our categories. And then we're going to split that out into a test set. And the idea is that we have this MNIST data that we have, and it actually has lazy evaluation. So even though I said, hey, let's use that MNIST, it didn't actually grab all that data. So it uses the notion of like, hey, I'm going to wait until I really, really need the data, then I'll go get the data. And so that's what I'm going to do right now is I'm actually going to tell it to load the data. And so this will actually evaluate the MNIST data and automatically split it into these two buckets, the training bucket and then the testing bucket. So that's pretty nice. Cool. So here's a couple other things. So here's our friendly library random, and you'll see why I need that for a moment. What I'm interested in doing is plotting the data. So it's always good practice when you're doing data science to visually inspect your data. You never really know what you get until you open the box. So that's what we're going to do right here. And this allows us to kind of plot the data. So that's what this import statement does. And what we're able to do then is call that plotting function and kind of grab some random digits to look at. Oops, wrong one. So there's a digit, there's another digit, there's a digit. And so you can start seeing that we see these different kind of digits, and we have some notion of the variability of the digits. So in this case, this is a 1 that's kind of leaning this way. The other one was leaning this other way. I'm going to say that's a 0, like that. We have a 1 that's more vertical. So the computer is going to have to start learning all the different subtleties of this data. But we could actually look and see that this data can be hard. So what we have right here is we have that scriggle. By a quick show of hands, is that thing a 4 or a 6? Who thinks it's a 4? I thought it was a 4. Okay, so I guess everyone thinks it's a 6? Okay, so apparently that. So what we can do is actually find it via 6. So some of these are a little bit difficult to do. Cool. So what we need to do now is we need to reshape the data. And so this is actually the hard work of machine learning now. So some people are the machine learning researchers, and the machine learning researchers are developing new algorithms and implementing those new algorithms. Most data scientists don't actually do that. Most of what data scientists do is define a problem, find the data, and then get that data into a way that the computer or the machine learning algorithm can understand it. And so that's called munging. And so that's primarily like what needs to happen. And so I'm going to kind of give you a flavor for that. So what we're going to do is we're going to take our X-train data, and we're going to kind of update it. And what we're going to do is we're going to reshape it. And what we're going to do is we're going to kind of take the old shape. So that's going to be X-train shape. And by the shape, it's just a matrix. So we have rows and columns, and we'll take the number of rows, and we're actually going to update that, and we want to make it into that kind of stretched vector, because that'll be easier for that to learn. And I forgot to define that. So, whoops, let's go up there, hit the wrong button. Okay, let's go. What I need to do is I need to find a thing called image size. And so that's how big it's going to be. And what it's going to be is that 28 times 28. And so I don't need to do the arithmetic. I can just define it as image size. Let's run that. OK, success, no typos. So far, so good. We have that data. We also want to do, so we want to update that. And we're actually going to have to recast it just because of the nature of the data. And so we have a built-in function called asType. And we're going to redefine it as a float with 32 bytes, like that. And then the last thing we're going to do is another little trick. It's called normalization. And so normalization is rescaling the data to be bounded between 0 and 1. And then that allows us, our machine learning model, to train a little quicker. So we got all of that. OK, that's good. So there's no need to watch me retype that. What we can do is just grab that code and do this, and then switch it for the test. There's the test. 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 There we go, success. Okay, one last step before we define the machine learning model. What we want to do is we need to actually convert the way the numbers come into our classes that the computers can read. So humans are very good at reading numbers, 1, 2, 3, 4, 5, 6, 7. Computers, not so good. So we need to kind of change that around a little bit. So let's do that. Y-train equals Keras utilities to categorical, and then we'll pass in the old wide train, and there was 10 of those. Okay, we'll do the same thing for test. Sweet. Okay. Cool. So now we're ready to, now we have the data, which is the kind of the start of it. We need to define the architecture of the deep learning framework. So we're going to go grab that. So from Keras dot models import, and the most common kind of model is called sequential. Sequential means that the data just flows, in this case, from left to right. So we're just defining a relatively simple model that does that. So it's an object-oriented model. So what we need to do is we have a class called sequential. We need to define an instance. We'll just give it a good generic name like model, and we'll instantiate that class. So we've done that. Cool. So we have the kind of placeholder. We said, hey, we have this model that flows left to right. But what we need to do now is define each layer of that cake. And so what we want to do is define that. And the simplest kind of layer is called a dense layer. So we can jump into layers, and then we can import a dense layer like that. And this is what it is. So this is like a bipartite graph that's fully interconnected. So it's saying that every node in one layer is fully interconnected to all the nodes in the next layer. And then it's just saying that, hey, we don't know what's going to happen in our data. So this gives us a lot of flexibility for doing that. OK, so now what we can do is define that input layer. So again, using this notion of object-oriented programming, we can grab layer.input, and then we have this class called dense. We need to say, hey, how many of those nodes? And in this case, we're actually going to call them units. So we are going to have 512 of those. It's kind of arbitrary. That's kind of the weird thing about deep learning. It's a lot of trial and error learning. So maybe later on, we might want to turn that down or turn that up. But we're just going to kind of start there. Then we need to define our non-linearity, which we call an activation function. And from the earlier one, I use that sigmoid. So that sigmoid is a nice kind of non-linearity, like, low values are low, then it gets pretty steep, and then high values are capped. And then what we need to do is define the input, and it's called input shape, like this, and image size, and we define it like that. That's good. Okay, so what we need to do, once we do that, we need to add it to the model. So we have our general instance of that model, and then there's a method on there called add, and we can just add a layer to that model. So we can just add that layer input to there. So now we've taken that instance and we've attached the first layer to that. Well, it turns out that it's actually much simpler to do this by composing it. So we can just say model.add, call in our dense class, and then we can call in, say, units 512, and then activation equals sigmoid, like that. And so this allows us to compose the model kind of very elegantly. So we're actually able to define very complex ideas in a relatively simple amount of code. Okay, so now at the end, we need some kind of output for that model. And so I'm going to call this layer output. Again, a dense layer, because that's the most common. In this case, we're going to pick 10 units, because there's 10 categories, digits 0 through 9. And we have another activation, which is another kind of nonlinearity. It's a slightly different kind of nonlinearity. It's called a softmax. Softmax allows us to map the neural network activation to our categories. That's all I'm going to say about that. Cool. So now what we're able to do is actually talk about our model and look at the summary. And so then this is what Keras thinks. And notice I made a typo. I forgot to add that output layer to my model. So let's add that. Layer output. Okay, now we go back over here, check out my model architecture. Okay, there it is. So that should be my model, like that. Cool. So now I have the general architecture of that. But this model doesn't know anything about the world. All it knows is that there's going to be this vector of inputs, which are going to be pixel intensities, and then the output is going to be these 10 categories. But we need to have some way of training that model. So that's what we need to do. So what we're going to do is do model.compile. And we're going to say, hey, how are we going to judge how wrong we are, which is called loss. Okay. And then we need to say, hey, how are we going to learn to get better? Called an optimizer. As Raymond mentioned, there's a thing called stochastic gradient descent. So that's what that is. And then we're going to say, hey, what do we care about? In this case, I just care about accuracy. Cool, we did that. Then we're at the last step. The last step is actually training. So what we're going to do is take our model and we're going to fit it to the data. So we grab the data, we fit it. And so in this case, it's going to be train y.train. Epochs is the number of times we look at the data. In this case, 5 is a pretty good number for the quick demo. We're going to keep a look at it by calling it verbose. And another machine learning term called validation, which is just saying, hey, let's take peeks at it and see how good we are. There it is. And so that's how you define a model. So we grabbed raw data, processed it up, defined an architecture, defined how we did training, and now the model is actually going to train if our fingers are crossed. But I'm going to skip ahead because I'm running out of time. So most of deep learning is just waiting for the model to train. So it's a good idea to get a hobby for that. Cool. I'm going to I'm going to skip out of this for now. We're just going to skip this. So that was kind of the step through of Keras. There's a lot of ways to explore this. There's a lot of different non-linearities or activation functions. There's a lot of different optimizers built in. This is just one type of architecture. There's other architectures. You can explore those. The thing I actually think is most powerful, there's pre-trained model. So someone's already defined a model and trained it, and you're able to leverage that existing architecture and weights automatically. And so pre-trained models are one of the cool parts of Keras because you don't necessarily have time to train your models from scratch every time like I did. So the idea is that Keras is designed for humans to do neural networks, not for computers. It's easy to do because you can just focus on what you want to do and not necessarily how it's executed. And hopefully I made it relatively painless to define a neural network. But by no means are we done. So the idea is that this is kind of just a start of this notion of neural networks. And so I would definitely check out the Keras docs. They did a good job. And then the blog is good. There's courses. And then also dig into deep learning, because this is just kind of the start of it. But hopefully this kind of gives you an end-to-end idea, and you can kind of go off on different rabbit trails to look for that. Thank you very much.
All right, we have time for a couple of questions.
Hey, Raul, what's it?
Raul.
Yeah.
So,
Yeah.
Great talk. Just wanted to ask, what are the trade-offs between additional nodes and additional layers? For example, additional layers tackles like non-linearity in data. So I was hoping you can discuss to the audience those trade-offs.
Yeah, generally, the idea is that what are the trade-offs between having a deeper network and a wider network? Generally, the network performs better. The wider and deeper it is, the better it performs, the longer it takes to train, because it'll have to understand and learn the weights at each one of those connections. So if we constrain the network to be very, very skinny and very, very shallow, it's less powerful, but faster to train. In general, training time is not usually a constraint, so networks are becoming incredibly big, and there's not really a huge, the trade-off of training time isn't a huge trade-off, so networks have just become bigger and bigger. There's one up here. I think I could just repeat oh, right here, okay, so.
Yeah, it's a two-part question. First is just a technical question about I noticed in the first layer, we defined 512 inputs, even though we had 784 input nodes. Was there some sort of implicit input layer there, or how did that work?
That's correct. There is an implicit input layer. Keras takes care of that automatically because it knows the size of the vectors, and so it makes sure that the matrix multiply is correct. And so we're just having an implicit input layer, and it handles that for us.
My second question was just about you mentioned how it's getting easier and easier to train big networks, but kind of what there is to gain from complexity reduction and in terms of greater interpretability of the models.
Yeah, so that's the big tough one. And so interpretability of this is becoming increasingly difficult because of the size of them. There's just so many weights. They're non-linearities. They're very complex. I'm actually just going to defer to my friend Sarah Hooker, who's giving a talk in the afternoon about model interpretability, and I'm going to leave it to her.
All right, one last question.
Yeah.
Overtraining.
Overtraining.
How do you deal with
Overtraining.
Yeah, so the concept is overtraining. And so just to define that real quick, a working definition of overtraining is that you've shown the data so many times to the network, and the network is so flexible that it's able to adapt and kind of memorize the data and know every little nuance of the data. And then when we give it new data, it says, I haven't seen that before. I don't really know what's going on. It doesn't perform very well. There's kind of two ways of handling that in neural networks. One is called early stopping. So right there, I trained it 5 times. Usually you train these thousands of times. You would just stop early. So if the things are not improving, you would just stop early and just say, hey, that's good enough. The second one is called dropout. Dropout is actually pruning the weights. So we had this dense layer that had all these weights. You randomly take away some of those weights every time you train. That makes the model more robust and stops the memorization process. So early stopping, just don't train as many epochs. And then for every epoch, randomly remove some weights and then reintroduce those later. Cool. that it?
One last
Oh, one last one.
Last
Oh,
one.
okay. Thinking-
So I've given people advice like start with scikit-learn and then
Yes.
explore the ideas and the algorithms, and later on you're going to learn a different API for actual production usage. It seems like the main benefit of Keras is that it's easy to use, but still based on TensorFlow.
Yep.
Do you recommend absolute beginners just go ahead and start with Keras?
I guarantee everyone to start with Keras. It's the simplest one. There's a lot of other great libraries out there. They have other good advantages. Like everyone's really excited about PyTorch. PyTorch is a great library too. But for beginners, Keras works really well. Then if you want to move to production, I actually used this to move to production at a company that I worked with last year. What happens is behind the scenes, it actually compiles the TensorFlow code. So then actually, if you ask Keras, say, hey, show me your TensorFlow code that you made on my behalf, it'll do code generation and hand you the TensorFlow code. That TensorFlow code then can be tweaked and changed a little bit to like optimize for performance. TensorFlow goes into production. It was designed to go into production very easily, and so you're able to put the TensorFlow code into production. So you can think about Keras as code generation. And so as a machine learning engineer, I was using it for code generation as fast prototyping, and then the final tweaks were done in the raw TensorFlow code. So it works well to start making that transition towards production.
All right.
Cool. Lunchtime?
Thank you very much. Yes.
Yes. Cool.